start the recording. All right, I'll share my screen and we'll get to work. All right. Okay, so this is this. And last time we were we started the topic of dynamics, right? And we were discussing forces and different various types of forces and all. Is there any question from anyone regarding dynamics, whatever we covered so far? So we started off with dynamics. We made a link between how we started off our course with physical quantities and then why we needed kinematics and then dynamics. We talked about force, what is a force in general, and then we talked about different types of forces with examples, right? Where we talked about contact, non-contact forces and all. So is there any question?
So I really do not get how like you said, electricity and magnetism, they can be like two, they are different, but yet they are the same thing.
They're two sides of the same coin, right? That's what you're asking. That's what you're asking,
Yes,
right? You did not understand why they're. You don't have to understand that really. You need a lot more knowledge to basically understand that concept completely. These two things, you're aware of the fact that there is something called electromagnetism, right? Electromagnetic force.
Yes,
the name of the force.
Yes,
it's really together. So the four forces of nature: we have gravity, we have electromagnetism, we have strong force, and we have weak force. These two forces, they are. Yeah, so they're just a single force really, or it's just a single field, which is really an electric field. But when you observe that electric field, relative to some motion, for example, you're moving, or to you it appears that the charges are moving. So if you're standing and it appears that these charges are moving, then you would observe magnetic field as well, right? And for example, suppose that suppose that if you're sitting on this positive charge, or suppose that you are that positive charge itself, then according to you, the charge, you are not moving, right? You're stationary because you're sitting on it. So your frame is the rest frame. These things are again very off topic, but in that case, it's not, you'd say that you'd not be really moving. You'd be standing still or stationary really, because it's the same example as if you're sitting in a car, right? And so according to you, there would be no magnetic field. But according to this observer who would see that the charge is moving, he would see that there is some magnetic field as well. So magnetic field really is the byproduct of a moving charge, really. So it depends on the different observers. Yeah. All right. So there is a lot of mathematics and details behind that, but we'll not get into that. You need the knowledge of special relativity and electrodynamics. So we'll just stop right there. Any other question from the last class?
No, sir.
Okay, no questions. All right. So then we'll proceed towards vector diagrams is the next topic. We covered these vector diagrams in physical when we were doing the first topic, physical quantities. Does anybody remember that? We talked about components of forces and all. Anyone remembers that? Who was present in the first classes? I was just the reason I'm asking this is really so that if you want me to go through it all over again, or should I skip it?
Sir, I prefer if you go over it.
Go over it again. All right. Okay. Amazing. Then we'll do that. Okay. So we'll talk in terms of vector diagrams for force. Now, force is a vector quantity. Do you understand what that means? Is that
yes, sir.
When I say
direction.
It has a direction.
in a very basic, exactly, right? So a very quick example, for example, if this is a box and I have to push it, suppose I'm pushing the box. If I push it in this direction, it will move over here, right? And now if I push it in this direction, then the outcome is different because the box will move over there. So if this force vector, if I apply this vector and the out in various ways and the outcome varies as well, in that case, I'll say that this quantity is a vector quantity, right? So the direction contributes something. The direction has a meaning, right? So in that way, force is a vector quantity. All right, now we can represent vectors. It's actually called representation theory of vectors. Representation of vectors. I'll just use representation, ignore my spelling, of vectors. So we can represent our vectors in multiple ways. Okay, so a way of writing a quantity, if I write force and I want to say that this is a vector quantity, then I'll just put an arrow on top of it like this. This thing means that this is a vector quantity, right? This arrow on top of it, that's what it means. I can draw this thing diagrammatically, and I can represent a vector with a line, and the length of this line is the magnitude or the strength of this force, for example. And then I can draw an arrow. This arrow points in the direction of where the force is being applied, the direction of the force, right? So the length of arrow is the strength of force. We're talking in terms of force at this point because we're talking of forces. But for example, if it was any other vector quantity, for example, velocity, then it would be the strength of velocity, right? How fast it is moving. And the direction of arrow, or you could just say the arrowhead, points in the direction of this force, right? Direction of force. So that's pretty simple stuff, right? Everybody's clear with this thing?
Yes, sir.
Okay, good. So far we have developed that force is a vector quantity which has both magnitude and direction. Now, I'm sure that you're all aware of this thing as well, that the units for force are kilograms, meters per second squared, which is given a new name, Newton, right? So that's these are just the units for forces. And now, suppose that I have, okay, I'm going to give you an example. You have a table in front of you, and suppose that you have a book lying on that table, right? I have given this example to those in the first lecture as well who are present. There's a book on this table. Suppose I apply a force on this book over here like this, and then I apply a force on this book like this as well. So upwards and to the right. What would you expect? It's an experiment. Just perform this experiment and make a prediction. What would you expect? Where does the book move in total? Like, what would be the result of applying these two forces simultaneously? What would you expect? Just do, if you have a book lying in front of you, just do the experiment and tell me what happened.
It would move towards the northeast
Diagonally,
direction.
right? And yeah, exactly. So it would move to the northeast direction. This one, diagonally. Right. Amazing. So you made a prediction, you see that's what happens, right? And you can make that prediction now because you're familiar with this. Now it's an everyday thing. And this is what happens. Now, suppose that I have so many vectors. Suppose I apply like this, like this, like this, and so many vectors. And I want to see what would be the resultant of this thing. Resultant meaning what would be the final result of applying all these forces together. If I can write down a rule, a general rule to add all these vectors, that's what I'm getting at. To add all these vectors, what would the final result of that be? If I have an equation or a method or an expression for doing that, then I can add many forces relatively easily, and I can tell what would be the resultant of that. So the goal is to add forces, sum of all the forces. This thing just means, for example, if I runs from 1 to some n, then this thing just means force 1 plus force 2 plus force 3 plus force 4, and up to so on, up to any number of force n, right? So is that clear? Is this notation clear for everyone, or did I confuse you?
Clear.
Okay, good. All right. So
But sir,
that's what we want. Yeah.
sir, can you just explain actually this equation one more time though? Because
Yeah, of course, I'll do it, no problem, right? So we can instead of writing this so many quantities like this with a sum, right? Writing 1 2 f1 plus f2 f plus f3 plus f4, who knows how many of them are there. We have a shorthand notation, it's called the sum notation, and this symbol means that I'm summing, right? I'm adding something. Now what am I adding? I'll write over here force, right? Force. Now
Is it a sigma?
how many force? Yeah,
That's a
sorry.
sigma, right? So that
Yeah,
symbol
it's
is
known
sigma,
as
right?
it's known as sigma, right? This is I think it's a Greek letter. I don't know, maybe it's a Greek
Yes.
letter. It's known as sigma, right? The capital sigma, really. Sigma. The capital version of that sigma, right? So yeah, that's what this symbol is. And so the quantity that I want is force, and now there might be so many of them, so I'll associate an index with it, I, and I'll say I'll sum I how many times. So I'll take I from 1 and up to, for example, if I wrote here 3, then that means I would run from 1 2 and 3. So there will be 3 forces, f1 plus f2 plus f3. So I'll write it like this, f1. So in first I write I equals 1, so that's f1. This sigma means sum, so okay, I'll add plus, then I'll add the other one, f. Now 1 has been completed. What's the next number? 2. I'll write 2, then again sum because of the sum notation, the sum sigma symbol, and then now f, and what would be I? 3, because after 2 it's 3, and 3 is the final number. So I'll just stop over here. I'll not add any more to this. So in that way, I wrote this thing where I said it runs to some number n. N can be anything. It could be any. This is the case where n is equal to 3, right? So n is equal to 3. So I add forces like this. Okay. So is that clear? I cannot hear you. Okay. Okay. Good. All right. So yeah. So that's this. Now this is a way to this is just a mathematical notation of summing your forces. How do I sum my forces graphically? I use the help of vector diagrams, right? So it's a graphical, GRAP, graphical. Okay. Yeah. So now suppose that I have a ball and I kick the ball, suppose like this, right? So this is my leg and I'm kicking the ball, and that means that I'm applying a force in this direction. And suppose someone also kicks the ball in some other direction. For example, suppose someone comes from here and kicks it like this at the same time. So then this will be the vector, right? So suppose this is force 1 by the first person, and this is force 2 on this ball by the second person. Now, I want to know if both those kicks were done at the same time, right? How would I add these forces to get a final resultant force? Direction and its magnitude as well. So it's very simple, really. What I can do is, there is this thing that you can do with these vectors. You can move them around. As long as I don't change the length of this vector and I don't change the arrow on top of it, I can, it's in when you do physics, more advanced type of physics, it's also given a name. It's called parallel transport. So I have to parallelly transport this vector anywhere, right? What that means is, so suppose that I take this vector. Now what I can do with this, I can play around with it. I can take it here, take it here, take it here. You know, if I take it, so I take it here, I take it here, I take it here, 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 here. Wherever I take it like this, you can see that the length of this vector did not change. The arrow on this vector will not change as well. It still points over there, right? So it's still pointing in the same direction. The direction is not changing. Wherever I move it doesn't matter, right? So what I can do is I can take this vector and put it on top of this. So I can join these two tails together, for example. I can do this. Now, this is known as a vector diagram, really. So now I want to add these two vectors. So this is F2. Now, how do I add these two vectors? The way to add these two vectors, it's called, I'll write over here, adding vectors. It doesn't matter, 2 vectors, 3 vectors, 4 vectors. I started with 1 and 2 vectors to keep it simple, and then we'll generalize it to n vectors, right? So what I'll do is I'll take this vector and sorry, actually, I'll give it a name first. The name is head to tail rule. Anyone of you have heard about this head to tail rule?
No.
Okay, so I'll explain it. What you do is, it's very simple. You just take a vector and you put this vector on top of the other vector's head, right? So what I've done is I've taken the tail of F2 and I've put it on the head of F1. So that's head to tail, right? So now you can see that this F1, the head is over here, and the tail of F2 is on top of the head of F1. Are you following along?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Okay, so that's head to tail, right? So the name says it all, really. So there is no complication in this thing. It's very simple. I'll put this on here, and now the resultant vector, let me use some other color. I'll use this blue. The resultant vector would be starting from this tail and ending at this head. So I'll draw it like this. Like this. So that's the resultant vector. Now let's see what that means, right? That means what happened to my colors? 1 second, let me just. Okay, so that means if I apply this force F1 on the ball in this direction, and at the same time someone also applies F2 on this ball in this direction, then the resultant of the force that would act on this ball would be in this direction. Now remember, I said I can parallel transport my vectors, right? As long as I don't change the length of this vector, I can move it around. So if I put it at the center over here, I can clearly see the direction the ball moves is in this way. So the resultant of F1 and F2 is this direction. Now, of course, directions are relative. Everything in this universe is relative, right? There's no absolute in this universe, except for the speed of light, by the way. Okay, so I'll just draw a horizontal line like this, and I'll measure the angle from this horizontal. And then whatever it is, let's just call it theta. I'll say that the direction of, let's call it Fn, the resultant, Fr, the resultant force. Direction of Fr is theta degrees from the horizontal, So that's how I'll write this direction of this vector. And now to compute Fr, I can do this 2 ways. I can do this mathematically, and I can do this by simply using geometry, right? Tools. I'll use a ruler and I'll define a scale, and I'll say that so let me write it over here. So 1 centimeter corresponds to, for example, 2 newtons of force. You could say something like that. So now that sets a scale, which means that if I draw a line of 1 centimeter, for example, this is a line of 1 centimeter, this line means 2 newtons of force. So that's what you mean by defining a scale for the system. So far, are you following along, everyone?
Yes, sir.
Yes, sir.
All right, okay, good. So now it's very simple, really, to using geometry to write down FR, right? What you'll do is you'll put a scale on this FR, you'll measure the length of this thing in centimeters. Suppose it's 2 centimeters, for example. Suppose that this FR comes out to be, this line is, you'll say that it's 2 centimeters. What that means is, if I use this scale, that 1 centimeter is 2 newtons, then 2 centimeters is 2 plus 2 newtons, right? So that's 4 newtons. So that's how easy it is to use this, well, I just call it geometry, geometrical tools to find the resultant force, right? And of course, how do you find the angle? You put a protractor on this thing like this, right? Of course, you'll put its 0 at this thing, right? So I'll use another color. So you'll put a protractor like this, right? And then you'll see that this angle from the protractor, and then you'll see what is over here. Maybe it could be 30 degrees, for example, right? For example. So then you'll say that theta is equal to 30 degrees from horizontal. So that's how you write down the, you find the resultant of forces. So is that clear? Using geometrical
Yes,
tools. Okay, all right, amazing. Now there's another technique for doing this. Another technique for adding vectors is using trigonometry. And God, I wish I had space over here. But I think I'll just take this thing on the next page. Just take this diagram, the next page, copy, paste. Okay, so here we have it. All right, so you just borrow some tools from mathematics, and in physics we borrow a lot of things from mathematics, really, and we'll just use trigonometry from mathematics, and we'll define how I want to write this force FR. So using trigonometry, we can say that FR squared is equal to F1 squared plus F2 squared. Now I can go into its detail as well, because but what you do is you use this triangle, because these vectors, you can draw a triangle using these vectors, really, and then you use the Pythagorean theorem to write down this relation. Now it's very simple. Now suppose that F1 is 1 newtons, suppose F2, for simplicity, right, it's also 1 newtons, then FR, the resultant squared, would be 1 newton squared plus 1 newton squared, which would be 1 plus 1 squared plus 1 squared is 1 plus 1, and that's 2. So that means that resultant force squared is 2, and the resultant force would be the square root of this thing, so it would be square root of 2. And of course, we have newtons, right? So this is Newton squared. All right. So that's how you can compute the resultant force using a formula, a mathematical expression, right? So this is that mathematical expression. I can generalize it to saying that FR squared is equal to sum I Fi squared, and I can run from whatever. So let's just say. So that's the generalization. Of course, you don't have to remember this generalized form. It's enough if you remember this thing. Now we have the magnitude now, right? What about the direction? how do I find the direction from mathematics? You'll use again trigonometry, and you'll use the sine cosines, right? Really, this thing that sine theta, sine square theta plus cos square theta is equal to 1. This expression will help us. It's an identity from trigonometry. I'll not go into its detail, of course, because that's the part of mathematics, really. And if I start doing all of the things, then it takes a lot of time. So I'm just going to tell you that if I want to find the angle theta, which this FR vector makes with the horizontal, I'll just say that that is theta is equal to tangent inverse of the y component of the force divided
Yes, he
by the
is.
x component of the force. Now, of course,
okay.
for this you have to understand what would be the y component of the force and what would be the x component of the force. So we'll get into
Drop your
that
nuts and move your
now.
butts.
Someone's mic's
This is
on.
so boring. This is so boring. This physics.
Array, your mic
Physics is
is
like
on.
the most.
Okay, so that's theta, right? That's the angle that this vector FR would make with the horizontal. Now the task is to find the y and the x component of the forces. So suppose I have this FR which pointed in this direction, right? So that was my FR. We have the coordinate system. A two-dimensional coordinate system have 2 degrees of freedom, which is vertical degree of freedom. This is a very weird line. Let me draw a straight line. And so that's usually called y. And the horizontal degree of freedom, let me just draw it like this, is this one. And it's usually called x. So here we have 2 degrees of freedom, x and y. And both of these degrees of freedom, x and y, are independent of each other. What that means is that there is no part of x that is in y, and there is no part of y that lives inside x. So if I have a vector that points like this, which is my FR, this vector has both parts, y and x. Now, what it means to write its components is to break this vector down into those 2 parts, those 2 independent degrees of freedom, x and y. How do you do that? Well, if this vector makes an angle theta with horizontal, suppose that's the angle theta, then I can say that the y component would be the completely vertical component, right? So that's in the y direction, and we give it a name f subscript y. And then the component that points in the horizontal direction, we give it f subscript x. Now, from mathematics and knowing some geometry, this angle is also this angle theta. So these 2 angles are equivalent or equal. Okay, now if that's the case, then I can use this thing that sine theta is equal to opposite by hypotenuse. Cos theta is equal to adjacent by hypotenuse. And tangent theta is, I think it's opposite by adjacent. You're aware of these expressions?
Yes, sir.
Yes, sir. Those expressions of trigonometry, right?
Yeah, exactly. Right. So you just borrow those from mathematics as well. We borrow a lot of things from mathematics, really, in physics. And so using that, I can write down fx. What would be fx? Fx, if I make this triangle, right? If I make this triangle, then this, let me draw it over here. This thing looks like this. I'll draw it over here separately, fy. Here I have fx. and here is this vector like this, right? So actually to make this triangle really, I'll use this vector FR, and suppose, well, I can draw it like this, FR, like this. Now, if this is angle theta, then Fx is what? It is FR FR,
Over
that
Fy.
because FR is right, and yeah, it times sine of whatever the angle is. And how did I write this? It's sorry, my mistake. I was right. It's cos of theta, right? And how did I write this? I wrote this using this thing, cos theta is equal to adjacent by hypotenuse, right? So what's adjacent? Adjacent is this thing, this Fx, and what's the hypotenuse? It's this Fr. So that's Fx by Fr, and then I rearrange this expression to get the value for Fx. Is that clear for everyone? Hello?
Yes, clear.
Okay.
Somewhat,
So,
sir. Can you explain this again?
Yeah, I'll explain it again quickly. Okay, so I think the confusion came from this thing that I did not draw this thing as a complete triangle. So I'll just do that. Remember, I can parallel transport my vectors. I can play with these vectors as long as their magnitudes and directions are the same. So if this is FR, this is Fx, Fy, I can just drag this Fy to this side and put it over here like this. So that's Fy now. And we remember the angle was this theta. This is the triangle. Now I can do all the mathematics in the world with this thing. And the mathematics I'm talking about is this trigonometry. So now see that suppose that I want to write a relation between Fx, theta, and Fr, right? Because Fr, we know, we have found Fr by this expression over here. Remember this one, right? This thing. Now, because we have found Fr, and I know theta and I know theta and Fr, then what I can do is I can just write Fx, or let me do it like this. Cos theta would be, remember, adjacent by hypotenuse. Adjacent is this thing, this line, which is Fx. Hypotenuse is this line, the slanted line, which is Fr, right? Now, I just have to do some basic mathematics, bring this Fr to that side, and this gives me Fx equals Fr times cos theta. So is that clear now? Is this clear, Hassan? Hello. Can't hear you.
Now it's better
Okay.
understood.
Yes, I get it now.
Okay.
Yes.
Amazing. Amazing. All right. So in the same way, I can write down Fy. There's less than 1 minute remaining. So I'd like you to do this thing on your own. Try to write Fy. What would be Fy? And in the next class, let me know what expression did you write for Fy, right? What would be over here? It says less than 1 minute remaining. So I think it's pointless to continue from here onward.